So we discussed about Maxwell-Boltzmann distribution, and we got a distribution function f of v dv. We're writing it as f of v dv, and that is 4 pi into m by 2 pi kbt raised to 3 by 2 into e to the power minus mv square by twice kbt into v square dv. So that was the distribution function, or it is known as the speed distribution function. Now suppose we want to calculate the average value of the speed. So we want to calculate this average value. So this average value will be given by, so any average quantity which is a function of velocity, you have to multiply with the probability distribution and integrate over all possible velocities or speed. So that will be equal to, so we take it out, 4 pi into m by 2 pi kbt raised to the power 3 by 2, and then you write it will be, it is a v here and there is a v square here, so together it will be v cube e to the power minus m v square by twice kbt and dv. So I'm keeping all the constants outside. Now this integrand we will just solve. So again, this is we'll just write it in terms of a gamma function, and the way we can write it is that so the term here is v square, so we'll write it as 2v dv, and then it will be to the power minus m by twice kbt, that is a into v square, and then we'll have only v square left here because I have already taken a v square here, and then there will be a half multiplied by all the constants which we have written here. Sorry, not here, this constant. Now this v square, now we have to write it as n minus 1, remember that. So it is basically v squared to the power 1. So what we can write it as, it is v squared to the power 2 minus 1. So it will be gamma 2, this integrand value, it will be gamma 2 divided by a to the power 2. And what is a? A is this constant m by 2 pi kbt, 2 kbt, sorry, m by 2 kbt and square of that. So what we see here, gamma 2 is nothing but n minus 1 gamma n, so it will be 1 into gamma 1, and gamma 1 is n minus 1 factorial, which is 0 factorial, which is nothing but 1. So we'll have only m by 2 kbt whole square, and inverse of that, that is the value of the gamma function. And we also have a half here. Let me write the constant now. So the constant was 4 pi into m by 2 pi kbt. I'm just writing it in a slightly different way, m by twice kbt to the power 3 by 2, and then there was a pi that I'm taking out, pi to the power 3 by 2. So what we get is this is equal to 1. So as you can see, m by 2 kbt, this is 3 by 2, and this is 2, means it is you can just write it as 4 by 2. So I'll be left with 1 m by twice kbt in the denominator, and so it is 4 by 2 and this is 2 by 2, so I'll be left with the square root of that, and then these 2 cancels with this. I'll have 2 here, and what I have is let us just see here, I'll have 1 pi to the power 3 by 2 here, and this is pi, so this will cancel, giving rise to 1 pi to the power half. So at the end of the day, what we are getting is I'll have 2 times pi to the power half and divided by m by 2 pi kbt, that 2s kbt, that we can write it as twice kbt by m raised to half. Then we can actually put everything inside the parenthesis, and keeping in mind that we have a power half. So if I put 2 inside, that will be 2, I can write it as 4 square root of 4. So this 4, and so instead of 2 I can write it as 4 to the power half, and then put everything inside. So it will be 8 pi kbt by m. I think the pi is in the denominator, not in the numerator. So it is divided by pi to the power half. So it will be nothing but 8 kbt by pi m to the power half. So this is the value of the average velocity. Now you can also ask, you can now plot it, the Maxwell-Boltzmann distribution, and now just ask this question: where basically what is the value of this all these parameters that we got? So if you plot the Maxwell-Boltzmann distribution, again remember that it has basically 2 terms, f of v dv, that actually goes as e to the power minus some constant into v square dv. So if I just plot f of v versus v, that's how it will look like. And then what we'll have is that, think about it, at v equal to 0, the function will be 0 because this term is 0. And when v tends to infinity, the function actually goes to 0 because of this term. So very high and very low velocities are actually, the probability of that is actually 0. So this function will look like something like this. And then what you get here is that you have something where somewhere the function actually picks up. Now remember that this is a speed distribution. If I had plotted the velocity distribution, which is f of vx that we discussed at very early, so that has a form of e to the power minus b vx square. So if I plot vx along this axis, remember that velocity can take both positive and negative values. So that function is known as Gaussian function, or this is sometimes known as it's a bell-shaped curve, and this it's called a bell-shaped curve. And here note the striking difference that I'm getting this term, v squared term, when I actually considered that this is a speed distribution which does not have any preferential direction. So that is actually changing the entire thing. Now we can actually proceed along the same direction and try to find out what is this maximum probability, or what is this maximum distribution, maxima in the distribution. So that maxima, to get it, you have to just take the derivative of that function with respect to velocity, and then to find the maxima you have to just take it to be 0. So you can easily get it. So there is some constant here, but we don't care because the constant will be anyway 0, because we are just equating it to be 0. So if I take the derivative, so follow it carefully. So it's a chain rule in differentiation. First take the derivative of e to the power minus bv square. So it will be just e to the power minus bv square, and it will be minus b, and times you will have e to the power minus bv square into derivative of v square with respect to v, so that will be 2v. So that entire term should be equal to 0. Now what you see here is a very interesting thing, that we have, if you look at it here, that if I take e to the power minus v square, v into e to the power minus v square common, then we'll have minus b into v plus 2, that is equal to 0. Now you have three possibilities. One is v equal to 0, that is just one of the minima, and the second possibility is e to the power minus b v square, that is 0. That happens when v tends to infinity. And the third thing, e to the power minus b square equal to 0 means v tends to infinity. So these are the two location of the minima. So this, the first minima is here, and the second minima is at basically at infinity. So you can actually draw it more nicely. Okay, so at very high value, so this is also the second minima. Goes to, it's not actually, the minima should not be here, actually it's just exponential square decay, so it is at tends to infinity, the very high value. And also the third condition is giving me that v is 2 by b, and remember what was b? B was m by 2 pi kBt, so 2 kBt, so it is basically m by twice kBt. If I just put it on top, that will be, it should be 1, let me just check quickly, it is 2v, and when I take the derivative, it is basically, yeah, so e to the power v square, when I take the derivative, I have to take also the derivative for v square, that will give me 2v. So what I can take as common is v, and this will be then, check once again, this will be then v square. Yes, it has to be v square, and this 2 will cancel, this will be just 1. And then I'll have v square is equal to 1 by b, so twice kBt by m, or we can say that, I can just write it here, that v is nothing but twice kBt by m square root. Now this v is, we write it as v most probable, meaning what is the most probable velocity. Now we see that you have three different kinds of velocities. One is the v square average, which we already got from kinetic theory of gases, and that we know that will be 3 kBt by m, but usually we take the square root of that because it has a dimension of velocity that is known as, this is basically mean square velocity, so taking the square root we call it as a root mean square velocity, that is square root of 3 kBt by m. And we just showed that the average velocity is nothing but 8 kBt by pi m square root. And then right now we showed there is a v, and I'm writing it as mp. Mp in the sense is the most probable velocity, or the it basically is the where the curve actually maximizes, and that is nothing but twice kBt by m, square root of that. So what we see here, so this is twice kBt by m, and then the 3 kBt by m and 8 kBt by m, I will just have a look at it. So 8 by pi, pi is 3.14, so it will be always greater than 8 by 3.14 will be greater than 2, but of course it is less than 3. So the average velocity will be somewhere here. So it will be higher than this value. So this will be the V average position of that. It's highly qualitative the way I'm writing it right now. And the RMS velocity will be somewhere here, which is the highest value. So you see that average velocity means actually what is the average number of molecules, or what is the mean of this distribution is lying. Now you can see that that actually depends on the area under the curve also. Now this is a probability distribution, remember that, and if I take the area under the curve, that should be always equal to 1, because we know that f of v dv, it's a probability distribution, integrated from 0 to infinity should be equal to 1. Now we can ask a question that suppose we go to a higher temperature, so what will happen? Or lower temperature. If we increase the temperature, you can see that the function goes as with respect to temperature, there is a functional dependence inside b, and there is also v square. Both of them actually are dependent on temperature. Now if you plot it, then you can easily figure out this curve will actually get more and more flattened, and this value of this most probable distribution will actually shift towards right, and all the velocities actually will shift towards right, and the curve will get more and more flattened, in the sense that but the area under the curve will still be the same. It will be still, if we integrate it, it should be equal to 1 always. So this is drawn at two different temperatures, say T1 and T2, where T2 is greater than T1. Now one more interesting thing to look at is this kind of curve, where actually I have two different functional variation. One is v square, and one is e to the power minus some constant into v square. So think about it. If I plot it very separately, e to the power minus v square will be very sharply decaying function of v, and v square actually goes as this. It's a quadratic function. So the product of them actually is something like this. So as you can see that e to the power minus v square picks up at v equal to 0. However, at v equal to 0 the function is not maximum because of this term is also there. So that is making the function at 0. Similarly, at a very high value, e to the power minus v square is 0, but v square is a very high value, but you don't get a very high value there because now this is basically bringing it down. So at somewhere here, where both the functions have some values, they actually get the maxima. Now similar type of behavior you will also see in many other situations. For example, when we will discuss in quantum mechanics, so when you study this hydrogen probability density or probability distribution along the radial coordinate for say 1s orbital, and the functional form for 1s orbital is the wave function. Actually it goes as e to the power minus r by a0. So if you go away from the nuclei, the electron, this is the basically probability amplitude decreasing. So square of the probability amplitude decreases as e to the power minus 2r by a0. Now that is a decaying function of r, that chi square, mod psi square, which actually is directly related to the probability density. However, you never get the maxima at r equal to 0, which is at the nucleus. The reason is you actually measure the probability density but not the probability. So which means so if this is the atom, you are talking about probability density as you go away from the nuclei. So you see that probability density drops, but when you measure the probability, you have to multiply it by a volume, and that volume means actually you have to consider a small sphere around it, and that volume of the sphere, or if you just go somewhere here, you have to consider again a volume of a spherical shell that we kind of calculated, and when you multiply the volume of the spherical shell, you remember that will come as 4 pi r square dr. We already calculated it in terms of v, that was 4 pi v squared dv, it is the same thing. So that actually is a quadratic function, and that goes as like this. So when you plot the actual probability, which is multiplied by force by r squared, so it's the volume, and this is the probability density. So density times volume is the probability. So you have two functions which are actually maximizing or minimizing at two different extremes. So what you see, actually, this function will go also as a with a maxima somewhere else, neither at r equal to 0 or r equal to infinity. And that for the 1s atomic orbital, you can easily show that this maxima will come at r equal to a0, where a0 is the Bohr radius, which actually Bohr found to be the radius of the electron, or the, if you think that, okay, so the electron is classically orbiting as a particle around the nucleus, so that distance is basically a0, known as Bohr radius. So that you can easily figure out from in quantum mechanics also. So this kind of curve come and many different places, also in degeneracy, or in the Boltzmann distribution. When you talk about rotational levels, there also you'll see that, okay, fine, if I go to very, very high rotational levels, that your Boltzmann distribution goes as e to the power minus e by kBt, that we discussed a little bit. So chances of getting a particle at a very higher level is much less, so it actually drops down. But the number of states are also increasing in a number of states for a particular energy, which is known as degeneracy factor. That also goes as it goes as some factor to 2j plus 1. We're not let's not go into the details, but the point here is that since that is also going high, you will get a increasing value of that, and together you'll see that these two functions actually goes through a maximum. So the point here, this kind of nature of the curve you'll encounter at many places, not only in Maxwell-Boltzmann distribution, but also in some other systems like rotational levels, when you are talking about probability distribution in the rotational levels, or even in particle in a box, also 3D box, when the degeneracy factor is increasing. So basically, the long story short, there are two always mathematical forms of the inside the function. One is trying to basically maximizing the function at 0 and minimizing the function at infinity. The other one has just the opposite effect, that the actual function is a product of these two parts, and which goes through a maximum. And now you can ask this question. So we got a function which is Maxwell-Boltzmann distribution function, or the velocity speed distribution function. Now, what is the meaning of this dv? So if I plot f of v versus v, so if I ask you what is the probability at of finding the molecule at v, that is not a very good question to ask. The reason is, as I said, that the exact number of molecules, those are actually fixed for a narrow range. You have to always, whenever you are talking about probability, you are not talking about this in the same sense like hydrogen atom. We are not talking about probability density. You are talking about probability, which is basically probability density times the volume. In this case, it is f of v is nothing but probability per unit velocity range. So what we talk about is, actually, to get the actual probability, you have to talk about probability in a narrow range, which is v to v plus dv, and that is this function. So this function will tell me the fraction of molecules, because this is still a probability. So some number of molecules divided by the total number of molecules. This number of molecules is nothing but the those number of molecules which whose speed lie in the range v to v plus dv at any time. And again, on statistical ground, we said that this number for a fairly large system will always be fixed, because some molecules are entering in this speed zone and others are leaving. So you always talk about a particular width in the distribution, and then once you integrate this curve, it is nothing but you take at various position of the v, and for every v you just calculate what will happen, what is the area element if I go from V to V plus dV, and in that way you basically build up the area under the entire curve, and that is the meaning of integration. And then you realize that f of V dV, so that is basically the area under this curve, and if I integrate over all the area, which means I'm varying now V from 0 to infinity, that should be equal to 1. So this curve is known as actually area normalized curve. Now the question is, from this distribution, can I actually get a distribution which actually say is in terms of the energy, something like this? Can I get it? So because that will be very useful to understand reaction kinetics or reaction dynamics, that when a reaction is feasible or not. Now to get that, we need to just use a very simple relation. We know that half mv square is the kinetic energy, and here energy means the kinetic energy itself. So wherever I have the v square term, I can easily replace it by this, and then you can easily say that so v square will be twice epsilon by m, or we can write it as v is nothing but square root of twice epsilon by m. So the speed distribution, we wrote it as, if you remember, that it was 4 pi into m by 2 pi kbt raised to 3 by 2 e to the power minus m v square by twice kbt v square dv. Now we have to replace these terms, so that we can write it as, I'm not right now writing this one, e to the power minus mv square. So you know that half mv square, that will be the kinetic energy. So this is nothing but e to the power minus epsilon by kbt. By the way, when I write epsilon and call it as a energy, it means that it is actually translational kinetic energy, always. So because it's a Maxwell-Boltzmann distribution of molecular speed, so it's a translational motion that we are talking about. And then instead of v square, we can directly write twice epsilon by m. And now for dv, we can write it when just taking the differential on both sides. So it is square root 2 by m into d of epsilon to the power half. So d of epsilon to the power half, if I take the differential, it will be epsilon to the power half will be square root of 2m. So it is nothing but derivative of this, or differential of this. So that is nothing but half x to the power half minus 1 into dx, something like that. So you'll get epsilon to the power minus half, and there's a half factor here, and d epsilon. So let us just put it here. So it will be half epsilon to the power minus half d epsilon, and in the front you have 4 pi into m by 2 pi kbt. Now if you just rearrange the terms, so that will be so look at it here carefully. So I have an this is raised to 3 by 2. Now this 4 pi, and there's a 2 here, so I can write it as 2 pi. Yeah, we forgot to write this factor here, square root of 2 by m. So it will be also multiplied by square root of 2 by m. And then you can see here this m and m to the power half is m to the power 3 by 2, and that will cancel with this m to the power 3 by 2. So what will be left with, and there is a square root of 2 here, and there is a 2 here. So I can write these together as 2 to the power 3 by 2. because these two I can write it as 2 to the power 2 by 2, and this square root of 2 is 2 to the power half. So I'll have 2 pi, and that 2 to the power 3 by 2 will also cancel with this 2 to the power 3 by 2. So in essence I'll have 1 over pi kBt raised to 3 by 2 e to the power minus epsilon by kBt, epsilon to the power minus half, and this epsilon will give me epsilon to the power half d epsilon. So that is basically the Maxwell-Boltzmann distribution of molecular energies. So let us write it clearly. So what we just got, that we got basically the distribution function in terms of molecular speed, that we write it as f of v dv, and that is 4 pi m by 2 pi kBt raised to the power 3 by 2 e to the power minus mv square by twice kBt into v square dv. And if I just convert it into the energy distribution, I'm writing as g epsilon d epsilon. So that is 2 pi into 1 by pi kBt raised to 3 by 2 e to the power minus epsilon by kBt epsilon to the power half d epsilon. And you see that this energy distribution is also will have a shape something like this. It has a exponentially decaying function, but it if I just plot it epsilon g epsilon versus epsilon, so there will be a decaying function, but that decay is not too fast decay like the Maxwell-Boltzmann distribution, and the rise is also not too fast. There actually it was v squared, square of velocity. Here actually it is epsilon to the power half. But the overall nature will be, overall qualitative thing will be same. It is one function that is rising with respect to epsilon, and the one function that is decaying. So it will have slightly different curve, which is something like that. But yeah, the qualitative nature will be same. So to summarize, so we have got basically two distribution functions. One is Maxwell-Boltzmann distribution function in of speed, and the other one is the energy. And we'll see how this energy distribution function will be useful in calculating or estimating the rate constant. And remember, that is our goal. We have to calculate this k of t, or this rate constant at as a function of temperature, and see what is happening.